Hello everyone and welcome to Team General Dynamics Electric Boat Consumer Off-the-Shelf Design of a Data Acquisition Systems ELE Computer Engineering Capstone Virtual Summit presentation where we'll discuss what the team has worked on and achieved over the past 2 semesters. My name is Luke Wilson, one of the electrical engineering students on this project, and I will be starting us off. While our technical directors have asked that we withhold their photos, Adam White and Art Viola have been an immense help to our team over the past 2 semesters. Adam and Art are both URI alumni, graduating in 2014 and 1984 respectively. Other than our technical directors, our team consisted of 4 members. We had 3 electrical engineering students, Luke Wilson, as you already know, Wilmer Chinchilla, and Daniel Kennedy. We also had 1 computer engineering student, Michael Marcello. Established in 1899 in Elizabeth, New Jersey, General Dynamics Electric Boat is a premier defense contractor for the United States government. They currently support 6 classes of submarine, including the Seawolf and Virginia class, while the Columbia class is currently in development. The motivation for this capstone project came from the desires of the students who wish to emulate the technology seen in self-driving cars utilizing a consumer off-the-shelf philosophy. Our anticipated best outcome is relatively straightforward. It is the successful design of a mobile data acquisition solution capable of receiving and storing sensor data that matches design specifications over a wireless connection utilizing several digital and analog in and out acquisition units. While our individual team members were able to achieve significant accomplishments for their focus areas for this project, we were unable to bring it all together at the very end to achieve complete functionality. Therefore, we did not achieve our anticipated best outcome despite our best efforts. So, what were we able to achieve over the past few semesters? Through both individual and collaborative efforts, our team was able to design, implement, and verify the functionality of all 3 PCBs, design a GUI, and implement 3D modeled hardware onto the RC car. Additionally, the team was able to interface with some of the sensors on the mobile platform and establish data communication between client and server devices. On the right, you can see the GUI and the PCB layout created by designer Chinchilla for the sake of Raspberry Pi connections. Simply put, this project has no potential economic impact as it evolved into a student-driven project outside of the scope of the original project pitch. As you already know, my name is Luke Wilson, one of the team's electrical engineering students, and I'm going to now discuss my individual achievements from the past 2 semesters. As you can see highlighted in red on this block diagram, my contributions consisted of working with the time of flight sensor and headlights at the front of the car. Additionally, I 3D modeled the hardware that we mounted to the RC car. While in early stages of this capstone project, I performed research on various alternative microcomputers and sensor applications. The majority of my efforts were spent on 3D modeling the system and designing the time of flight and headlight PCB, the schematic of which you can see on the right-hand side here. Early on, I researched microcomputers such as the Udo Bolt V8 and the NVIDIA Jetson Nano. However, due to both hardware limitations and budget constraints, I determined the Intel NUC and Raspberry Pi 4B would be more than sufficient for the team's needs. The NUC was also eventually swapped out to a comparable Windows PC. Now we'll talk about my portion of the PCB design. Pictured below is a 3D rendering of the 2 circuits. The top portion consists of the time of flight sensor application circuit, which takes 5 volts from the power distribution PCB to feed the sensor. Data is then fed via SPI to a peripheral evaluation board, which can then be sent to the AFBR S50 series Explorer API on a PC. The bottom of the right-hand image is the relay-based headlight circuit, accepting a GPIO signal to activate the relay that allows voltage to flow from Daniel's power distribution unit to activate the headlights. Full functionality for this PCB was achieved. However, the peripheral board was not able to be interfaced with, so we were unable to achieve data collection from this sensor. I also 3D modeled the mountable components in Inventor 2022. From the beginning, our team knew that we would need to be able to securely mount all of the hardware components to the RC car in order to ensure the design of a secure embedded system. Therefore, I volunteered in order to fulfill this role. On the right-hand side, you can see the 3D assembly of the different components. This was extremely useful in determining the layout and measurements of the team system, given very limited available space, and this saved us a lot of time when it was determined that we needed to start bringing everything together. The solution I came up with was a result of our team's need for modularity and ease of testing, ensuring that we could remove any component at any time with relative ease and address potential issues. The other images illustrate how the system came together once everything was 3D printed. You can see the time of flight sensor mounted to the front of the car in the center of the screen. Next, I am happy to introduce my fellow designer, Wilmer Chinchilla. He's one of my fellow electrical engineering students, and he also designed the Raspberry Pi connection PCB and worked on many of our visual aids.
Highlighted in red is everything that I have covered. In particular, I focus on the interface between the Raspberry Pi and the other sensors on the board. So in terms of my technical accomplishments for the entire year. Looking back at fall term, it was really just a multitude of making sure that we have everything we needed. As a result of the proposal set by the team by General Dynamics, we were in charge of very customizable but very open-ended project. So we ended up deciding on basically on an RC car system that drove around with sensors, and we would then input and output signals and such. So we needed to come up with a finalized list of sensors, and that's where this comes in. Mainly, we decided on the accelerometer, a gyroscope, a GPS, a photoresistor, and a temperature sensor. Now, all these sensors come with their own various functions, and we needed to make sure that they did what we wanted them to. So we needed to come up with a functional block diagram and coming up with spreadsheets and figuring out that they work as they intended. So again, for my second point, that is what I discuss. And then in terms of that, to designing stage, it took quite a bit of time. So we didn't really get started with a lot of the later processes until about a couple months in. But spring semester is where a lot of it was just applying what we had and making sure that we were building to our needs. And so towards the end of fall semester and the beginning of spring semester, it was mostly just designing of a central Raspberry Pi printed circuit board. Now this board is supposed to, it has a couple of functions mainly. One is direct connection to the Raspberry Pi. So every other connection from the whole system is going to be fed through the board and then placed onto the Raspberry Pi. This helps with breathability and making sure that we know exactly where every connection is going. And so as the Raspberry Pi has 40 header pins of GPIO, my board would have a direct connection to those 40 pins and then feed those GPIO connections out throughout into the system. Now, as opposed to the whole process itself, it did take some time, given that we were all relatively new to Circuit Maker, and as Daniel was the only person who had taken the PCB course or was taking it at the time. It was a bit of a process, but we eventually ended up getting everything that we needed to, including the schematic, the design layout, making sure that all the connections included data transmissions, as well as making sure that, again, like all those external sensors that weren't on my board were connecting to the Raspberry Pi. And along with that came a whole bunch of troubleshooting, making sure that every connection and every trace was going where it had to. This was, again, a first time for a lot of us, so it was a bit of a process, a couple of hiccups, but ultimately we came out with a project that I say shows what we learned. And up next is Daniel Akanavi. He is another ELE student, and the main reason that all three of us could get our PCBs up and running.
Hello everyone, my name is Daniel Akanavi and I'm one of the electrical engineers on this project. I'm responsible for the PDU, which is currently highlighted in the red box. Here is a list of the things I'm responsible for. Collaborated in the early research and finalizing the list of sensors, sourced the batteries and battery monitoring system, responsible for the PCB design for the power converter with the battery monitoring system, soldered components with interface connections, and I'm happy to say the PCB board is successfully supplying 5 volts. Okay, so here's an updated schematic for the PDU, or rather the power converter board. To the left, we have our 9.6 volts in red. That's coming from our battery. It goes down all the way to F2. F2 is our fuse, which is supposed to protect the board, it's protecting the board from the load coming from the battery. In orange, we have our current sensing unit, which is the Adafruit sensor, and that's to measure the currents coming from the battery. And in yellow, there's the Texas Instrument chip, which is the main converter. We have some capacitors, inductor, and the voltage divider there, and it goes all the way to the green units through the bypass capacitor, which is C5, and to our interface connections J3, J4, and J5, which is a USB-A connector. In this slide, we have a 3D layout of the power converter board. If you can see, 9.6 voltage from a Traxxas battery goes into J1, and in our output switches J5, J4, J3, and J2. J5 is the USB-A connector that goes to the Raspberry Pi. J4 is the PCB for the Raspberry Pi, which has the accelerometer, gyroscope, and GPS. J3 is for the time of flight PCB. And J2 is where we do our current sensor, where we break the circuits to measure the current from the battery. Up next is our computer engineer, Mike Marcello, who is responsible for the GUI drafts, communications implementation, and systems implementation.
Thank you, Daniel. To remind you of what our system looks like, here's a block diagram. Specifically, my accomplishments are circled in red. Notably, I allowed us to interface between the Raspberry Pi and our Windows PC using the wireless access point. To delve into some details on the progress that I made during my time with the ELECOMP Capstone Design program, I would like to point out that I accomplished data communication between the Windows PC and the Raspberry Pi using the socket package in Python. We were able to use this method to communicate various sensor data, in which I was able to implement using the GPIO pins on the Raspberry Pi. The data was communicated using a comma separated string, and that string was then parsed by the Windows machine. This data was then displayed on the graphical user interface, in which it had applets for the various sensor data. I also assisted my fellow team members with the power distribution, which was critical in order for our sensors to be able to be utilized. I also assisted with the physical installation of the various 3D sensor mounting solutions, as well as installing the various sensor equipment. As I previously mentioned, one of my key accomplishments was establishing communications between a client and a server. In this situation, our client is a Windows PC and our server is a Raspberry Pi. This was established using the Python socket package, which allowed us to have TCP communications over a wireless access point. Notably, this wireless access point was used so that we could have extended range between the PC and our mobile solution, which is the Raspberry Pi mounted to the RC car. The reason for the use of the Raspberry Pi is so that it can communicate with the various sensors that we have implemented. They use various standards such as UART, SPI, and I2C to communicate its respective data to the Raspberry Pi. The Raspberry Pi will then have its own Python program to gather that data, interpret it, and send it to the PC and communicate as needed. Another one of the key accomplishments that I met during the program was the creation of a graphical user interface. I used Python's tkinter package to display various data such as an accelerometer, different system warning icons, information about the RC car battery, a control system for the headlights, as well as an ambient temperature gauge. These can all be controlled using the application controlled interface, or more simply a menu, and allows the user to be able to view and monitor the system status of the RC car. The most important feature of this application is that there is a video stream which allows the viewer to have a first-person point of view of the RC car and where it is going. This is accomplished using the ImageZMQ package in Python, which sends individual JPG images over a data stream and displays them as a video on the Windows PC. Other solutions were attempted, but this was found to be the most efficient use of our time. Thanks for watching. We'd like to give a special thanks for our program director, Dr. Sunak, for without him we'd have no ELECOMP Capstone program. We'd also like to thank our technical directors, Art Viola and Adam White, for their guidance along the way as we created and assembled our RC car project. We'd also like to thank Mike Smith for his help with the printed circuit board design, as well as the University of Rhode Island as our host institution for allowing us to have this program. And also thanks for Merrick Leach for his guidance with the RC car application. And finally, we'd like to thank Professor Yanaho Young for his advising on the sensor power distribution.